Hey everyone, and welcome back to Pod 4 Journal Club. All right, today we are tackling one of the biggest, most fascinating questions in AI right now. When we ask a model to show its work, to give us its chain of thought, what is really going on inside that digital mind? Is what we see the real story? Let's find out. It's kind of like this. Think back to math class. A student hands in their homework. The answer is right, and all the steps leading to it look perfectly logical. But did they actually use those steps to solve the problem? Or did they maybe find the answer some other way? I don't know, a calculator, a friend, and then just write down a plausible-sounding story to get full credit? Well, that exact same question is what researchers are now asking about AI.
Okay, so here's how we're going to break it all down in this explainer. We'll start by digging into this core mystery of an AI's secret thinking. Then we're going to line up the suspects, three competing theories for what's really happening. After that, we'll look at the evidence from the lab to see which theory wins. And you'll see there's a bit of a twist. And finally, we'll talk about what this means for how we study AI from here on out.
Okay, let's dive right in. What is this central mystery that's got the AI world so captivated? So here's the thing. Pretty much everyone agrees that giving an AI more time to think, letting it generate those intermediate steps, helps it get better answers. That part's not up for debate. The real mystery, the harder question, is why. What are those performance gains actually evidence of? Is it because the AI is truly reasoning through the words it writes, or is something else, something deeper going on?
To get to the bottom of this, the researchers say we have to pull apart three key ingredients. First, you've got S, for surface traces. That's the stuff we can see, the actual chain of thought text. Then there's Z, for latent states. You can think of this as the AI's hidden internal scratch pad, where all the messy behind-the-scenes calculations happen. And finally, there's B, for serial compute, which is really just the raw amount of processing time and power the model gets to use.
All right, so we've got our clues, S, Z, and B. Now it's time to line up the suspects. The paper presents three totally different theories, each telling a unique story about how an AI really thinks.
First up, we have what the paper calls H2. And honestly, this is the one that probably feels the most intuitive. It's the what you see is what you get theory. It basically says that the written-out chain of thought is the reasoning. The AI is literally thinking out loud, and the words on the page are its actual thoughts. Simple as that.
Next in the lineup is H0, and this one's a totally different angle. You could call it the "it just needs more time" theory. This theory argues that the content of the thoughts, whether they're visible or hidden, doesn't really matter that much. The performance boost just comes from giving the model a bigger computational budget, more time to crunch the numbers. The more time it gets, the better the answer will be. And our final suspect, H1, is maybe the most intriguing. This is the hidden inner thoughts theory. It suggests that the real heavy lifting part of reasoning happens deep down in those hidden latent states, that internal scratch pad. The chain of thought that we actually get to read, that's just a summary. It's a partial report from the front lines. And sometimes it's not even a very faithful one. So let's just pause and look at this side by side, because it really clarifies the whole debate. For the surface theory, H2, the visible text, is driving everything. For the compute theory, H0, it's all about calculation time. But for the latent theory, H1, the hidden states are the real star of the show. Understanding this core difference is absolutely crucial for what comes next. Okay, we've got our three suspects lined up. Now for the fun part. Let's see what the evidence says. The researchers ran some really clever experiments to put these theories to the test and see which one holds up. And the verdict from the lab? Well, it's not what you might expect. It turns out there is no single right answer. In a fantastic twist, the paper reveals that the best explanation actually changes based on the kind of problem you're asking the AI to solve. Context is everything. And this table just lays it out so perfectly. For what the paper calls ordinary reasoning, your standard everyday problems, the hidden inner thoughts theory, H1, is the winner. But for what they call constitutive tasks, where the AI is forced to follow a visible plan, like using an external tool, the what you see is what you get theory, H2, suddenly takes the lead. And for really, really hard problems that are more like a brute force search, it's H0, the just needs more time theory that explains the results best.
But here's the main headline, the big takeaway from all their tests. While it's not always true, the paper concludes that for most normal, everyday situations, the hidden inner thoughts theory is by far the most powerful explanation. The real action, most of the time, seems to be happening in those hidden states we can't see. Okay, so H1 seems to be our front runner, but hold on. It's not quite that simple. Let's really dig into the details of this complicated verdict. So the big argument the paper makes is this. From now on, our default assumption, our starting point for understanding these systems should probably be H1, the hidden inner thoughts theory. But, and this is a big but, it's not the whole story. We have to recognize that there are situations where that theory just doesn't fit.
So, when do these other theories actually come into play? Well, H2, the surface theory, wins out when you specifically design a task that forces the AI to depend on its written output, like making it use a calculator based on the numbers it wrote down. And H0, the compute theory, wins when a problem is just so incredibly complex that it basically becomes a search problem, and the only thing that really helps is throwing more raw processing power at it.
All right, so this all leads to the big question. What does this all mean? What do we do with this new knowledge? How should this change how we actually study AI from now on?
And look, this isn't just some abstract academic idea. This has huge, real-world consequences for how we study and ultimately how we evaluate AI reasoning. The paper leaves us with two key recommendations for the entire field. First, it says we need to change our focus. Researchers should stop being so obsessed with just the final text output and start treating those hidden, latent state dynamics as the primary thing to study. Second, we need to improve our methods. We need to get a lot smarter with our experiments so we can actually isolate and tell these three factors, S, Z, and B, apart from each other.
So if you remember one thing from this whole explainer, let it be this. To truly understand these powerful AI models, we have to look beyond the words on the screen. It's like trying to understand the ocean by only looking at the waves on the surface. We need to invent new tools, new kinds of submarines, to explore the hidden depths where the real thinking is actually happening.
And that really leaves us with a massive and honestly kind of unsettling question for the future. If an AI's real reasoning is buried deep inside a complex, hidden world that we can't directly see or interpret, can we ever truly understand why it makes the choices it does? And maybe more importantly, can we ever really fully trust it? I'd love to know what you think. Is this a solvable engineering problem or a fundamental barrier to trusting AI? Let me know in the comments below. This has been Pod 4 Journal Club. I'm host speaker. And hey, if you enjoyed this deep dive, make sure you like and subscribe for more explainers on the biggest ideas shaping the future of AI. Thanks for watching.